Now let's start taking a look here at example number 1. We'll see an easy example here of how we can apply this integration by parts formula. Our goal is always going to be to try to understand how we can look at a given integral and see a u portion and a dv portion. And if I can see those individual pieces in my integral and label them appropriately, I might be able to find all the things I need to fill in the other side of this equation. So just for the sake of simplicity, let's suppose that I kind of get us started here. Let's suppose that I state that u is going to be equal to, for this question, the value of x. Okay, so I'm just supposing that that x is a green piece, right? It's in the spot of u. Then I could state that everything else in my integral is a part of dv. So I'll say that this is going to be my cosine of x dx. Notice that I've kind of separated my integral into all green and red items. I didn't leave anything out, and dx had to be a part of one of those groupings. So with this, I can then easily start to see how I would find the derivative of u. Well, the derivative of u here would just be 1 times dx. I can see over here that if I was to go ahead and kind of divide over my dx, I would have the derivative of v with respect to x is equal to cosine, and that should give me that v is something that I could take the derivative of to get cosine. Well, that would be something like the sine of x. And now since I have this u, v, du, and dv all identified, I could start to say that by integration by parts, and feel free to use this abbreviation in your work, it's very common for me to use in mine, is I can state that the integral that I started with should be equal to, and I'm just going to fill in this formula. Whatever I labeled as u should be multiplied to v, so u was x and v was sine of x, and then I should have subtract an integral of whatever v was times whatever du was, which was just 1 dx, or I'll just write dx. So notice we haven't yet answered the question, because while we know that this integral is equal to all of this, we still have another integral over here to evaluate. And remember that we're going to keep our fingers crossed and really hoping that that's an easy integral to work with. Fortunately here, it is a very easy integral. What can I take the derivative of that would get me to an answer of sine? Well, yeah, I would have to do negative cosine of x. Notice that this negative is from up here, so when I put my extra negative on the front, it's really going to change this to a plus. Of course, since this is an indefinite integral, I will make sure to remember that at the back, I should have a plus c. And so I've arrived at what I believe to be an antiderivative for my function x times the cosine of x. Now, the important thing to do here is to make sure that we understand, how could I check that I'm actually right here? I mean, how could I actually confirm that I did this correctly? Well, if this is supposed to be an antiderivative, I could check by actually doing a derivative. That is, I could check to see what happens if I take a derivative of x times the sine of x plus a cosine of x plus a c. Now, of course, I mean, what are the chances, right, that I take the derivative of this and it ends up as that? No way. Well, let's just see how it plays out, I guess. I'll have to start with the derivative of x times the sine of x. That would involve a product rule, since those things are multiplied. So I'll start with derivative of x, which is 1, and leave the sine of x alone. Then I'll add on, leave the x alone, and take the derivative of the sine, which is going to be cosine of x. Right? Then I'll be able to go down here, and I'll be able to say that the derivative of cosine is negative sine of x. The derivative of my constant c is just 0. And see, obviously, there's no way that this gets me back to x cos... Oh, no. Look what we have. sine of x and negative sine of x are going to cancel out, and so I do just end up with x times the cosine of x. This actually works. I can find something that when I take its derivative, it actually produces this result. This is the valuable thing about this integration by parts formula. If I think about any other way of trying to compute this question, it becomes very difficult, right? Like, what else would you use? This isn't a derivative rule by itself. There's no u substitution I can do here, and there's no easy way I can think of algebraically rewriting this. So this integration by parts becomes extremely valuable. Now, I'm going to go ahead and ask you really quickly to identify that up above, I started the problem for you, right? I made it easy. I said, I'm going to tell you what to pick for the green stuff and the red stuff. And you might have been asking yourself the question, Kyle, how did you know what to pick for the green and the red? And the tricky part there is that experience really had to guide me there. But you can see what would happen if instead you were to select different pieces as the green piece and the red piece. In fact, I'm going to ask you to go ahead and to think about what would happen if you had your same integral, but you highlighted these pieces in red and green, you labeled them so that they were different than what we did up above. What if you labeled out the green stuff as the cosine and you labeled the red stuff as everything else? Could you see how you would actually be able to use this approach and get down to this integral and see what you would get on the other side? Right now I'd like you to try to pause the video and see how that would work out. And when you hit unpause, you can see me going through my solution. Okay, so I'm going to go ahead here and just quickly write down that if u is equal to the cosine of x and dv was equal to x dx, then du is negative sine of x dx, and v, let's see, I would need something I could take the derivative of to just get x. Well, that could be something like 1/2 x squared. So, by integration by parts, my integral x cosine x dx is equal to, and there's absolutely nothing wrong with writing this, u times my v. Since the order of multiplication doesn't matter, I'm going to put my x's first. So there's my u times v minus the integral of my v times my du, which is my sine of x dx, and oh, it was supposed to be a negative sign. I'm going to go ahead and bring that all the way out front so I have it out here. I'll just change that to a plus. Now, is this a true statement? Yes. But is it a helpful statement? Well, I would argue no. While it's true, this new integral that I got over here almost seems harder than the one that I started with. So this might be an indication that I might want to actually go ahead and try to rethink my selection for u and dv. Now, the reason that I ask you to work through a question like this right at the onset is to recognize that we may not always make the right choice when selecting u and v. There's a little trial and error in this approach, just kind of like there's trial and error in making a u substitution. You might try something, it might not work the first time. But if you start to see that maybe your integral is becoming harder, as opposed to up above where I had an integral that looked like it became easier, it might be something to consider of trying to swap around what you've selected as u and v. Now in the next couple examples, we'll see how integration by parts can be used on some other sorts of functions, but as well, we're going to have to constantly come back to this question of how do I know what to pick for u and pick for v? Our basic idea is always going to be that I want to pick something for u that's pretty easy to take a derivative of, and for dv, I want to pick something that's easy to find an antiderivative of. Outside of that, experience is often going to be our best guide.